All right, let's talk about pi. And I know what you're thinking. 3.14, circles, middle school math class, right? But what if I told you that number is so much more than that? It's actually one of the biggest mysteries in mathematics, a number that has completely obsessed some of the greatest minds for, get this, over 4,000 years. So think about this for a second. What could possibly connect a perfect circle, a totally random experiment with needles, and the actual physical laws of our universe? Well, the answer, believe it or not, is pi. This one single number just weaves its way through everything, from pure geometry to the laws of chance, and even into the physics that holds everything together. So let's unpack how that's even possible. Our journey starts with the central contradiction, this thing that makes pi so utterly fascinating. I like to call it the perfect paradox. I mean, on the surface, the definition couldn't be simpler, right? You take any circle, I don't care if it's a coffee mug or the orbit of a planet, and you divide its circumference by its diameter. The answer is always pi. It's this perfect, universal, unchanging truth. But here's where it gets weird. That's the paradox. A circle is, well, it's perfect. It's a finite, complete shape. And yet the number that defines its very essence goes on forever. Its decimal just keeps going and going with no pattern, no repeats. This beautiful, kind of baffling contradiction is what kicked off a 4,000-year-long chase to try and pin it down. So how exactly did that chase play out? It's a really cool story that basically mirrors how we, as humans, learned to think, starting with just practical, everyday needs and evolving into pure abstract logic. Now, what's so wild about this timeline is just how much it speeds up. I mean, look at those huge gaps early on. We're talking more than 1,500 years between the Babylonians and Archimedes. Then, as we get new mathematical tools, the pace quickens until suddenly, boom, we hit the modern era where supercomputers are adding trillions of digits to the record. It's an explosion of discovery. As you can see, the early folks, like the Babylonians and Egyptians, they just needed a good enough number for building things and farming, and you know what? They got pretty darn close. But the first real revolution in how we think about pi, well, that came from the ancient Greeks. The absolute genius of Archimedes wasn't just that he got a better number. It was that he came up with a bulletproof method to prove just how accurate he was. He decided he was going to literally trap the true value of pi. And this is just so brilliant. Look at his method. He drew a polygon inside a circle and another one outside it. Simple enough. He knew the circle's real circumference had to be somewhere between the perimeters of those two shapes. But then, here's the clever part. He just kept doubling the number of sides, from a hexagon to a 12-sided shape, then 24, and so on. And with every step, he squeezed pi into a smaller and smaller and smaller range. After doing some ridiculously difficult calculations, and remember, this is all by hand, no calculators, he finally stopped at a 96-sided polygon, and that was enough to make his groundbreaking proof. So this is the crucial point. He didn't just give an estimate. He gave a provable range. He guaranteed with absolute certainty that the true value of pi was trapped between these two fractions. This was a huge leap forward. It was a shift from just finding useful numbers to establishing pure logical truth. For over 1,500 years, Archimedes' method was the gold standard. But the next big shift totally changed the game. With the invention of calculus, we got these things called infinite series. And that moved the problem from geometry, from drawing shapes, to pure analysis. I mean, imagine getting closer and closer to the true value of pi just by adding and subtracting an endless, but predictable, series of fractions. No polygons needed. It was a way more powerful approach. Okay, so this is where the story gets even weirder. As we got better and better at calculating pi, a much deeper question started to pop up. What kind of number is it, really? For centuries, people hunted for a magic fraction that was exactly equal to pi. You know, like 22/7. If they found one, pi would be what we call a rational number. But if no such fraction existed, it would be irrational, its decimal just marching on forever into infinity without ever repeating. Well, in the 1760s, a mathematician named Johann Lambert finally settled it. He proved pi is irrational. And this was a massive discovery. It meant there's this fundamental disconnect between the perfect, clean geometry of a circle and the tidy worlds of whole number fractions. But wait, it doesn't even end there. It turns out pi belongs to an even stranger, way more exclusive club of numbers. So take the square root of 2. It's irrational, sure, but you can still capture it with a simple algebra puzzle, right? You can just ask, what number when you square it equals 2? Easy. But pi transcends algebra. There is no finite puzzle like that using whole numbers, where pi is the answer. And then in 1882, Ferdinand von Lindemann delivered the final stunning proof. Pi is transcendental. It can't be captured by any of those finite algebraic equations. This was just a huge moment for math. And get this, it had this incredible real-world consequence. It definitively proved that the ancient Greek challenge of squaring the circle, trying to draw a square with the exact same area as a circle using only a compass and a straight edge, is totally impossible. Lindemann's super abstract proof had just solved a 2,000-year-old geometric puzzle once and for all. Okay, for this last section, we're going way beyond the circle. Because honestly, the strangest thing about pi is how it just shows up in places that seem to have absolutely nothing to do with geometry at all. It's kind of like a cosmic ghost in the machine of the universe. Take rivers, for example. There was this beautiful, elegant theory that the average sinuosity of a river, that's just the ratio of its curvy, meandering length to its straight-line distance, should average out to be pi. And it kind of makes sense, right? A curved line divided by a straight one. But when scientists actually went out and measured hundreds of real rivers, they found the average was actually closer to 1.94. The theory was gorgeous, but the real world is just messier. It's a perfect little story of how science has to test these beautiful ideas against cold, hard data. But even if it doesn't show up in rivers, pi does appear with this almost eerie precision in other, totally unexpected places. You'll find it in probability theory, in an experiment called Buffon's needle. It's in the bell curve that governs statistics. And yes, it's buried deep inside the physics of gravity and the totally bizarre world of quantum mechanics. And this, to me, is the most profound part. Pi is literally written into the source code of our universe. It's right there in the fundamental equations for electromagnetism, for quantum uncertainty, and even in Einstein's theory of general relativity that describes the shape of spacetime. It seems like any time a physical law involves cycles or spheres or waves, pi just appears. Which really brings us to a final mind-bending question. This journey to understand pi took us from a simple circle all the way to the very fabric of reality itself. It's a number that is somehow both perfectly defined and infinitely complex. So if pi is truly a fundamental constant of our cosmos, you have to wonder, what other secrets, what other messages might be hiding out there, buried somewhere in its endless, random-looking digits?